name's McGinn, and I'm president of Solving Tornadoes, and the mission of Solving Tornadoes is to solve tornadoes, to understand them. And we're not really going to be discussing tornadoes in this little talk. We're going to be discussing H2O. And the way that relates is to understand tornadoes, you have to understand H2O first, because tornadoes are actually a function of the surface tension of H2O. Now, the reason this hasn't been discovered up to this point is because we just don't yet understand H2O, but I'm going to solve that now. I'm going to solve what's referred to as the anomalies of H2O. And solving the anomalies of H2O mostly has to do with a concept that's called incidental symmetry, and that's the name of this presentation right now. So let's get started. This is a gentleman named Philip Ball. He is a journalist. He's an expert in water. Or I should say, he is like the leading journalist in the world with respect to what's referred to as the water structure problem. The water structure problem is basically everything that we're going to be discussing here, and that is the fact that H2O molecules collectively have a lot of behaviors that are not well understood. These behaviors are referred to as the anomalies of H2O. This is a little YouTube video encapsulating our current understanding of H2O and hydrogen bonds.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Thank you, YouTube. I am largely in agreement with everything that was mentioned in there, except for this very last one, in which they make claims that are just simply absurd. That explanation they provided did a really good job of explaining why H2O is a polar molecule, but that did nothing at all to explain things like it says here. And then it says several other unusual properties. Well, you know, there's a lot of unusual properties about H2O. Here's how many more of them there are. There's 70 different anomalies of H2O, and as it says there in the red, that's 10 to 20 times more anomalies than any other common molecules. So again, this is Philip Ball. The common assumption that water is well characterized has led to explanatory edifices built on shaky ground. In other words, you're kind of already seeing a little bit of that. This common assumption that everyone wants to think, oh, water is simple, water is well understood. Two types of asymmetry, or what we call lopsidedness, really, that are associated with H2O molecules being a polar dipole. And it's really important to understand only if the actual atoms on the molecules have what we call a stretched electron cloud is any kind of a molecule polar. There's actually 2 types of electron cloud stretching on the H2O molecule, and one of those types is associated with the hydrogen atoms, and the other type is associated with the oxygen atom. The first type I would simply refer to as simple asymmetry, in other words, simple lopsidedness. Again, that's associated with the hydrogen atoms, And then there's tetrahedral asymmetry, and that's a more complicated form of asymmetry, or a more complicated form of lopsidedness. Here we're looking at the H atoms on there, and you'll notice right here we have a stretched electron cloud on that hydrofluoride molecule there. And over here on the water molecule, we have two locations where that's taking place. And that stretching only happens because of the electrical gradient that's displayed right up here. So keep those factors in mind. Now we're looking at the oxygen atoms here. And what you'll see there is there's two locations where we have an electrical gradient associated with that oxygen atom. And that means that there's two other locations where there is no electrical gradient. And that actually results in some of the electron clouds on the oxygen atom being pushed out here. And we're representing that here right literally with showing that these electron clouds are stretched. They're out of sorts with the nucleus of the oxygen atom. And that's referred to as tetrahedral asymmetry. Now, there's an underlying logic to that that has to do with the arrangement of electrons on this size of a molecule. On this size, I'm talking about the oxygen molecule, but it also applies to nitrogen, it applies to fluorine, and it even, in a sense, applies to carbon. If there is no stretching of electron clouds, then there is no polarity, and there are no polar forces. And that's important because it's the polar forces that are keeping the H2 molecules together. Okay, now we're going to talk about two types of symmetry, the opposite of asymmetry. Asymmetry being lopsidedness. Symmetry is, not lopsided. It's even. It's balanced. So these are two types of symmetry that are not associated with H2O, and I want to make that clear. These are not associated with it. Well, why are we talking about them, right? Because this is about H2O. Well, this is going to give us a very good frame of reference for understanding the type of symmetry that is associated with H2O. So there's two types of, just as there were two types of asymmetry, one for the hydrogen and the other one for the oxygen, there are two types of symmetry. In this case, one for the, again, for the smaller molecule, and the other one for the tetrahedral molecules. Now, this is an example of simple symmetry. This is just two oxygen molecules connected into an O2 molecule. This is the type of oxygen that's in our atmosphere. And you see that there's no stretching of electron clouds and there's no imbalance of electronegativity between these things. Now let's take a look at something that's a little bit more complicated, and that has to do with what we call tetrahedral symmetry. There's our methane molecule, and for instances of asymmetry, in a sense, there's actually an electrical gradient happening between the hydrogen atoms and the carbon atom. But here's the big takeaway from this. The methane molecule is not a polar molecule. Now you might wonder, well, if it has electrical gradients, how is it not a polar molecule? Because the arrangement of these electrical imbalances are themselves symmetrical. Methane molecule is a nonpolar, non-dipole. Here's a really good concept to be aware of. Let me get this in the right color here. These essentially, we can think of them as canceling each other out. These two cancel each other out, and then these two cancel each other out. Now, actually, on a tetrahedron, that isn't perfectly accurate. They don't exactly cancel each other out because they aren't exactly opposing each other as it appears on this paper. But the idea is, though, that since the methane molecule's asymmetry is arranged symmetrically, it's not a polar molecule. Here's a very important concept to keep in mind. With H2O, if there is no stretching of the electron cloud on the oxygen atom, then there's no polarity and there are no polar forces. So if you can stop the stretching of the electron cloud on that oxygen atom, you essentially turn off any forces that are occurring to hold the molecules together. So keep that in mind as we move on to the next section, because that's a very important concept. Now we're getting right to the heart of one of the longest standing mistakes in all of science. And this is literally Pauling's omission. This is what Pauling mistakenly omitted when he introduced the concept of hydrogen bonding between water. There's two types of symmetry associated with H2O that up until now are unknown to science, and they're actually very simple. It refers to symmetry that occurs outside of the structure of the molecule of H2O. And I guess that's where the confusion is. Somehow people miss the fact that this was something that coming from outside the molecule, and they, for that reason, I guess, made a huge error. Notice that right here we have two polar molecules. We have a fluorine, and we're trying to focus on that little H molecule, that dark blue one there. And see what happens when they come together is that the stretch of the electron cloud in that H is alleviated, and the reason it's alleviated is because of an opposing electrical gradient. We're going to show how these opposing electrical gradients literally cancel each other out, and it's simply a function of the fact that they're opposing each other. This neutralizes the electrical gradient and takes away the stretching of the electron cloud on that hydrogen atom. Is no longer a polar molecule in this instance because of this incidental effect of the other fluorine molecule completely neutralizing its polarity. Electrical gradients coming into the scene here. Little diagram here. Again, it's just the simple thing of drawing a line between that cancels out that cancels out that. Again, these things cancel out, and so here is polarity being reversed by a hydrogen bond.
So we're starting out with a very polar molecule right there in the center of the screen. We're going to see it turn from being polar to being nonpolar. Here we go. And there we have our very nonpolar H2O molecule in the middle of the screen. And the reason for that is because of the 4 hydrogen bonds that now surround it. It now has a tetrahedron surrounding it. We see there, a tetrahedron now surrounds that oxygen molecule.
And so what I'm saying is that these are essentially one and the same. On the left-hand side there, we see incidental tetrahedral symmetry. On the right-hand side, we see tetrahedral symmetry. Now, what's different about the incidental tetrahedral symmetry is it happens as a result of a hydrogen bond. It happens as a result of forces that come from outside the molecule. The purple here is the molecule, and the forces that are causing it to neutralize its polarity are coming from outside the molecule. They're coming from hydrogen bonds of other H2O molecules. Here are a few facts about incidental symmetry, and this is incidental symmetry in general, not just the tetrahedral, which we were just looking at. But incidental symmetry is intramolecular. In other words, it takes place between molecules. It is extremely common. All our oceans, lakes, and rivers are filled with examples of incidental symmetry. It is almost completely unrecognized by science. Now that's a strange one. Doesn't science know everything? Well, apparently they don't know this. There are two forms of incidental symmetry: simple, which has to do with the hydrogen atoms, and tetrahedral, which has to do with the other larger atom that is attached to the hydrogen atoms. And water is one of them. There's others too. There's associated with nitrogen, fluorine. They are also polar molecules, and they also have this ability to neutralize each other's polarity. And it isn't quite as comprehensive as it is with H2O, though, because those other molecules are less balanced. H2O is very balanced in terms of its negative and positive charges. One of the questions that comes up when you're trying to assess the magnitude of H2O polarity and polarity neutralization through hydrogen bonding is what is the scope of this influence, and how, to what degree do these molecules influence each other and change each other's polarity. So that's what we're going to discuss here, the grid of relative polarity neutralization. We have a situation where we're just pretending that one is removed, and that means that as it's removed, its polarity neutralizing effect on the surrounding molecules that it was bonded with disappears, and therefore there's going to be some reactivation of polarity in those, in those molecules. Here's one here, here's one here, here's another one. This is a molecule, this is a molecule. These are 4 different molecules here whose polarity has in some way been affected by the fact that it's no longer has the hydrogen bond associated with the molecule that is no longer in our picture there. We can ask some questions now. What is the scope of this influence? Obviously there's going to be some polarity activated, but how widespread is that? Is it going to, if we were to draw a circle around the influence of that change in polarity, there's a number of different circles. We might say, is this the circle that matters? Or we can say, would it be one that's more inclusive of the full molecules? Or is it even bigger still? What is the scope of polarity neutralization or polarity activation with breaking of hydrogen bonds? Well, these are basically the options. The options are that when a bond is broken, the activation of polarity can be on the bond itself within the molecule, that one little part of the molecule. It could be the molecule in its entirety, or it could be groups of molecules. Well, I'm going to choose number 2 there. I'm going to say that polarity has to do with the molecule in its entirety, but I don't think it's number 1. Number 1 seems to not be associated with what the evidence indicates, which is the anomalies of H2O. It seems to affect the whole molecule, and it might actually even affect groups of molecules more comprehensively than I'm indicating here. But you know how it is, you have to, sometimes just for clarity's sake, you have to choose one road and go down that road. So there's a picture of an oxygen molecule, and we're going to say that every time a bond is made on this, about 25% of the polarity of the whole molecule is altered. So this H2O molecule in our picture has no hydrogen bonds, so it has 100% polarity. If it had one additional bond, it would have 75% of its polarity. If it had 2 bonds, it would have 50%, on, kind of like that. And this sets up what I refer to as the grid of H2O molecules, relative and incremental polarity. And we're saying that, you'll notice there, we're referring to the number of bonds on each H2O molecule. It can have anywhere from 0 to 4. And I'm saying that within that, there's a continuum of polarity associated with it. And obviously, the greater are the number of hydrogen bonds, the lower is the polarity, all the way down to 0 when there's 4 bonds. Now, when there's 0 bonds, when it's essentially talking about a steam molecule, you'll have a very highly polar molecule, as we show right here. And in the middle, though, you're going to have a bond that still has two connections to other H2O molecules, and it's going to still have 50% polarity. And that is essentially where we get the structural strength. And that also exists when there's 3 bonds and when there's 1, 2. But keep in mind, when there's 1, there's no connection to anything else. So there's not really a lot of connectedness as you go farther left on this scale. And there's not a lot of polarity when you go farther right. So there's kind of a bell curve of structural strength associated with H2O. And that bell curve the point of that bell curve is right around 2. So the more connected are, the more H2O molecules are half connected, the greater is their structural strength. And that's because when they're fully connected, they have no polarity. And when they're completely unconnected, well, they're just unconnected. So they don't have any connectedness. Now I'm going to very quickly talk about surface tension and why surface tension exists in H2O. Surface tension exists because along a surface, there's restricted ability to achieve comprehensive hydrogen bonding. So there's still going to be, so you're going to have a lot of H2O molecules that only have 3 connections to other H2O molecules, not 4. And because of that, 25% of their polarity is going to be activated. And because of that, there's going to be some degree of hard bonds associated with this. And that's what we're representing there. A surface restricts the ability of bonds to be comprehensive. And therefore, there's polarity, residual polarity associated with the fact that you can't have complete comprehensive hydrogen bonding to neutralize all of the polarity. So the polarity literally emerges on the surface. And that's what happens with water. That's why H2O has that amplified surface tension. So we have 3 different models prior to quantum mechanics, after quantum mechanics. That's the current paradigm there, after quantum mechanics. And this new model that I'm introducing now, which indicates variable polarity and polarity that's reactive to the degree that it's bonded. These are the anomalies we're going to be considering. One of them is simply the very low viscosity, very high fluidity of H2O as a liquid, the high melting, freezing temperature of H2O, the high boiling, condensing temperature of H2O, the high heat capacity of H2O. And that's a big one because that seems to have a lot to do with all kinds of things. Including life, anything that has to do with energy, and that heat capacity plays a big role. And also the high surface tension, that has to do with the fact that H2O has kind of a hard phase hidden inside of it. And we're going to discuss exactly why that hard phase does exist. And well, let's just get on with it here. So the first model of H2O that we're going to address is the one that is kind of like the standard one you assume before you actually look at it too closely. And that's essentially what was happening up through to about the 1800s and up till about the 1900s. Water was basically ignored or dismissed as being unimportant, and it was assumed to be very simple. And then around 1910s and 20s, they started to become more aware of some of the unusual properties of H2O. And that had more to do with the fact that they were more aware in general of other molecules, things like CO2, things like the different gases in the atmosphere, oxygen and nitrogen, and other things like methane. We became aware that all these things, which have similar weights to H2O, actually have much lower boiling, melting points and freezing points. And not only that, but these melting, the boiling point and the freezing point is often only separated by about 20 degrees or so. With H2O, you have a very high, relatively high freezing, melting point, and you have an extremely high boiling point. And there's 100 degrees difference between the freezing point and the boiling point for H2O. And so all of these things make H2O stand out. So how does it square out when it comes to addressing these anomalies? Well, it only really addresses the high fluidity of H2O. That's the only anomaly that it seems to be consistent with, in that if you have a molecule that has very low forces happening between it, you expect it to be very fluid. And the other ones here, though, the unusually high melting, freezing, the boiling, the specific heat capacity, none of that had, this model just simply did not explain any of that. Now we're moving into the model that is currently the accepted model. This is the current paradigm, and that is simply that H2O is a polar molecule. And as you can see there, we have it all described exactly why it's polar, and it has to do with the electronegativity differences as we've discussed. But let's see how it fares in terms of how it addresses these different anomalies. Well, first thing that comes right off the bat right here is that it does a very bad job of explaining the one that the previous model did a very good job of explaining, and that is the high fluidity, low viscosity of H2O. And if you think about it, it really doesn't make sense that now you have a molecule that you recognize has these forces that are causing it to be attracted. You expect it to have high viscosity, low fluidity, and we just simply don't see that. Now, it does do a better job of explaining the unusually high melting freezing temperature in comparison to things like methane, and the unusually high boiling condensing temperature, again, in comparison to things like methane and CO2 and all that stuff. Now, there's nothing in here, though, that really explains why there's a 100-degree difference between the boiling point and the freezing point and the boiling point, so that really isn't well explained. And then further, as you go into the other ones, the heat capacity and the surface tension, well, it kind of gives you some indication as how these might be partially explained, but it really doesn't explain these very well at all. And unfortunately, this is something that science has kind of repressed. They've kind of all just pretended like H2O explains these things, but it really doesn't. And we kind of explored that in one of the original slides on this, where we talked about how they basically just make claims that are just simply untrue. A polar molecule, all it's really saying is that these molecules will have a tendency to stick together. Now, if they have a tendency to stick together, why does it not stick together in terms of viscosity? I mean, if you look at specific heat capacity too, and that involves movement, and there's space between molecules, and there's constant movement going on, that's the mechanism of its heat capacity. But saying something's polar doesn't really answer that question, which is kind of the theme of this whole talk here. So this is our current paradigm here, and these are the things that the current paradigm, the people who are managing it, I guess you could say, academia, is kind of repressing. They're not being fully honest with us about the fact that the current paradigm just does a lousy job of explaining some very basic observations. I mean, the one that really jumps off the page here is the low viscosity. I mean, how do you go from, you say, oh, we have a polar molecule, but look, it has such low viscosity. I mean, it plainly doesn't explain that, but they've somehow managed to get the public to, they've gotten the public to get their attention off of this fact, and they're addressing the things they do know, which is what happens in science all the time. They emphasize the things they know, and the things they don't know, they kind of, oh, that's not important. And let's see now, first let me kind of explain what my model is. This new model suggests that H2O polarity is highly variable, and that hydrogen bonds themselves are the mechanism of this variation. In other words, the more hydrogen bonds there are, the more that polarity is literally neutralized, as I've described here. And so let's see how it does in explaining the various anomalies. Well, look at that. It got 5 out of 5. It explains the unusually low viscosity as a result of the fact that when you have comprehensive bonding, you have zero polarity. And so the more fully bonded these are in liquid water, that's what you get, and that's why liquid water is such low viscosity, such high fluidity, because there simply it's not a polar molecule when it's in the liquid form. It's literally not a polar molecule. That under liquid conditions, where there's nothing inhibiting the achievement of hydrogen bonds, there will be a very low polarity, and as such, there's going to be very high fluidity or low viscosity associated with water, and that explains why H2O has such low viscosity. And there's a really good concept to be aware of right here, and this will kind of help you understand why this new model does such a good job of explaining what the previous model didn't. And that is a notion referred to as Coulomb's law. Now, Coulomb's law says that when molecules come together, that the closer they get to each other, the force increases. In other words, it's an inverse square force that has to do with getting stronger as they get closer to each other. Think of it, that's the same thing with gravity. But the observation, though, that for some reason H2O molecules aren't always seen stuck together like this. Instead, there seems to be some space, and there's a lot of movement associated with that space. Well, this explains it. This says that as these things move closer together, the polar force associated with the electrostatic force that's bringing them together is literally switched off. Literally switched off, at least when all four of them make a connection. And then as for the unusually high melting freezing temperature, well, the freezing of H2O is a little bit tricky. It's been severely misunderstood by the current paradigm, which wants us to believe that these things line up into a lattice, and for some crazy reason that no one's ever explained. The truth is they don't really line up into a lattice. What's actually happening is they're actually bond breaking, and that bond breaking is essentially activating enough polarity to create a structure, and that's why ice exists. We can even think of ice as being a situation where there's a bunch of surface appearing within the structure of the ice. And by the way, that's why ice expands. That's why it's less dense when it's freezing, because there's all this surface that's been created as these things kind of grind together and don't quite match up correctly, and they twist each other and stuff, and it creates all this surface within them, and that surface is essentially the thing that is essentially causing the hardness, because when you create a three-dimensional surface, you essentially create three-dimensional surface tension, and that's really what's happening in ice. So polarity is activated with freezing in some way, and that polarity is activated because when you do have freezing, they start to grind up against each other and they start breaking bonds. But that's getting a little bit ahead of things. Then we get to the high boiling condensing temperature of H2O. And this is actually a relatively easy one to see why this model works better than any other model, in that to get that high boiling, to really remove H2O molecules from each other, you have to fight every single level of polarity all the way up to the 100% to that flash point. And then we get to the specific heat capacity, and this is where this new model really shines. Now, here's a concept that I think you have to understand the importance of how this new model really does address the heat capacity, or really does explain what's going on with H2O. And that is, the reason H2O has a high heat capacity is because, well, let's just say that it didn't neutralize polarity right here. Well, according to Coulomb's law, when there's a force existing between water molecules, they stick together, because Coulomb's law says the closer they get to each other, the higher is the force that's keeping them together. And that's true for any electrostatic charge, including polarity. Polarity is just an electrostatic charge. So, but what's really happening with H2O is when they get to this point, comprehensively, you know, with four bonds on each of the H2O molecule structure, when it gets to this point comprehensively, the force that's holding them together is literally neutralized. It's turned off. So Coulomb's law does not apply to H2O when it's fully bonded. And since Coulomb's law doesn't apply, and since there's essentially no force here, what happens when they get to this point? Well, they bounce. And what happens to any energy? It too is conserved. So that's what happens. And then what happens when they get away from each other? Well, the polarity returns again. And that means that the energy is going to be, can't ever really get away. It's pulled back again. Force is turned off, and so you have this bouncing going on with H2O. And that's actually what you see. That's actually what you see when you actually look down and see H2O. You see this constant movement going on. It's a pendulumic thing, and it just goes on and on and on. When these things come together, they don't just stick together. The force is turned off. Coulomb's law does not apply because there's no force. And so what happens when they hit? Well, they bounce. They bounce. And that energy doesn't get passed on through the molecular structure. Instead, it results in a whole bunch of bouncing going on. And that's what we're seeing within water, and that's why water has such a high heat capacity, is because there's constant movement. There's constant, this absorbs the energy and increases the force. The force comes together, and the force is put to zero. Therefore, the energy is conserved. And so you get this kind of an activity going on inside of water. And that is the mechanism of H2O's high heat capacity. And then we get down to the unusually high surface tension. Well, I'm pretty sure I've explained that previously, but I'll just do it again briefly here. H2O surface tension is simply a function of the fact that along the surface you can't quite get comprehensive hydrogen bonding. Therefore, there's a whole bunch of the molecules there that have 3 hydrogen bonds. They don't quite have 4. Having 3, they have 25% of the polarity, and that means the force associated with any bonds existing along the surface is going to be greater. It's going to be at least 25% polarity, and they're going to make actual hard bonds. And that's why H2O has the high surface tension. It's because there's literally hard bonds along the surface, and that those bonds are literally a function of the fact that its polarity is not fully neutralized as it is below the surface. Below the surface, there's almost zero polarity. And so that puts it all together. This is why H2O has the unusual anomalies it has. It isn't just a fluke of nature. And this is the central truth. This is the thing that science missed up to this point. It's very simple. It's just that individual water molecules, when they make hydrogen bonds with other molecules, the bonds in their vicinity become weaker. And conversely, when they break bonds, the bonds in their vicinity become stronger. And that is the central truth of H2O, and that's what makes it so unusual, and that's what sets it up for all these unusual characteristics. So, if someone asks you, why does H2O have so many anomalies? It's not simply because they're a polar molecule. That doesn't explain anything. The reason H2O has all these anomalies is because it's a polar molecule, and it's a polar molecule that self-neutralizes its own polarity through hydrogen bonding. That's why water is unique. That's why water is special. And that's also why so many of the qualities of water are amenable to energy. And we just touched on one of those right here. We talked about how when these things come together, the force that's bringing them together is neutralized. And as it's neutralized, the energy associated with that movement is conserved as they bounce. They bounce away from each other. Now, there are other types of kinetic energy in the atmosphere, specifically spinning. And spinning is what underlies the basis of the vortice of tornadoes.